Welcome to the New Quantum Era. I'm your host, Sebastian Hassinger, and this is the podcast where I bring you conversations with leading researchers in quantum information science and technology. Today's episode comes to you from Albuquerque, New Mexico, where I'm attending the IEEE Quantum Week for 2025. This annual event, officially the IEEE International Conference on Quantum Computing and Engineering, or QCE, has actually become one of my favorite conferences in the quantum field. The organizers have done a really fantastic job bringing together engineers, computer scientists, and the broader physics community. That intersection, that interdisciplinary interaction is so vital because the cutting edge sort of science advances in quantum information need to be paired with robust engineering in order to achieve sort of larger scale, more reliable devices, and also to find applications in various fields for those devices. So next year's conference will be in Toronto. I'm already looking forward to it, actually. This is the last day of this year, and I'm thinking about next year's already, which I think is a testament to the quality. So special thanks to Carmen and Hausi, who helped arrange space for me to record the interview that I'm going to bring you today. My guest is Dr. Xiaodi Wu, Associate Professor at the University of Maryland in the Department of Computer Science. He is also a fellow at the Joint Center for Quantum Information and Computer Science, or QUICS, and an Amazon scholar. He's collaborating closely with the Amazon Bracket team part-time, and that's actually how I got to know him personally through our interactions at AWS, although I did know of him and I was following his research when I was still at IBM. Dr. Wu's work and his group span a broad range of projects at the intersection of computer science and quantum computing. With a background in both fields, Xiaodi has been focused on uniting the strengths of each domain to solve meaningful problems. In this episode, we're going to dive into his group's recent release from 2024 of SimuQ, which is an open source domain-specific programming language which is designed to make quantum simulations more accessible and productive and easier from an end-user perspective. Given that the most likely near-term applications of quantum hardware is going to be simulations of systems from nature, quantum systems, the timing and the focus of this work is especially relevant. So we're going to talk about quantum simulations, about SimuQ, about programming languages, about his own unique career path, and the challenges and opportunities of quantum simulation and the evolution of programming languages themselves. So I hope you enjoy the conversation. I sure did. Xiaodi, thank you very much for joining me. We're at the IEEE Quantum Week in Albuquerque. Thanks to the organizers for getting us this room to record. You've been in the field for a long time, and you've been involved in a lot of different really interesting projects. I wonder, can you start just by sort of telling us like a brief introduction and how you got to where you are right now?
Okay. Yeah. Thanks for having here, Sebastian. Actually, we also work together at Amazon.
That's right.
Information. Yeah. So, thanks for everyone listening to the episode. I'm Xiaodi Wu, currently our associate professor at the University of Maryland. I'm part of the QUICS, which stands for Quantum Information and Computer Science, which is joint center with between NIST and the UMD.
Right.
So I think I got into the field at the very early. I mean, for me, in my undergrad, when that's around 2004 or 5. At that time, I got into the program back in Tsinghua, where I studied mathematics and physics, which very science oriented, right? So I did had experience, do a lot of programming, computer science stuff in my high school. So right I got admitted to the program. Andy Yao, who is Turing awardee, and he returned back to Tsinghua. And he actually, I think he started all the field about theoretic computer science in China, because before him, nobody really, know that field in China.
Right.
So he has done a lot of introductory courses into the field. I'm really lucky to get into that, his course and learn about all the stuff. By the way, also lucky enough to get to the lecture by Chen Yang. He only did one lecturing in China on fundamental physics, and I'm really lucky to sit in his class as well.
That's cool.
And so, but then I quickly realized I want to do something that is computer science plus physics. And what's cool about that, right? So that at the time there is a concept of quantum computing, which is exactly computer science plus physics.
Yep.
So I don't think I really spend much time thinking about why I want to get in the field or what are the other alternatives. It's just very natural for me.
Right.
I want to do something under this interdisciplinary field. And maybe as I, going to see my, the research trajectory, I really enjoy being interdisciplinary, and maybe too much interdisciplinary for now. Yeah, so
it's always a trade-off, isn't it? Because you bring different perspectives to sort of cross those boundaries.
Yeah.
But also, it can be a challenge to keep focus on one thing to get deep enough to actually really make a fundamental contribution to that specialty. Right?
Exactly.
Yeah.
But I think my experience. I say I was really lucky to really get in the field, and also just witness the very huge growth of the field in the last decade.
Yeah.
And that also is the reason I can work in a very interdisciplinary way.
Yeah.
So when I I finished my undergrad in Tsinghua and got into the United States. I went to University of Michigan. I worked with Yao Yunxi. By the way, he actually now left Michigan. He's working in industry now. And
where is he at in industry?
He was the lead of the Alibaba quantum lab, but the whole lab has it's gone now. So, but I think he's just continue working some other way, which I'm not entirely clear about. Yeah, but that time, I am very motivated to study the intersection of theoretic computer science and quantum. I think that's still a super niche field at the time, and quantum computing wasn't a real thing. Nobody knows. There isn't any machine.
Right.
And I think even at that time, a lot of techniques we're seeing today, like superconducting, transmon, they're just invented. So nothing. Really.
When did you do your PhD? When did you finish it?
I got into the program in 2008.
Okay.
And then 5 years in Michigan.
Yeah. Okay.
So by that time, I was really into theoretic computer science, and actually, I did a lot of complexity theory. Start with my work. Basically, I did a summer intern with John Walters.
Okay.
And that time, the biggest thing about starting the complexity for QIP in the quantum interactive proof system. And the summer I got it there, they actually had a big breakthrough. That's the QIP equals p-space result. But before I know about that, I look into the problem. And I have my, a separate, thinking about this. I actually didn't tell John that I'm working on a little bit on that. I'm working on something actually much simpler, less ambitious with John. And actually, we didn't publish anything on that either. But then I tried to just think this for myself. And actually, right after the paper appeared online, I just talked to John. So I have something different from what they have. I think it turns out to be, I think conceptually simpler proof.
Interesting.
So there is a paper I read, about that, but it's something people already show.
Right.
Yeah, but just it's concurrently. I didn't really ask him about what he's thinking about. So I think this independently, but just he had a paper before me. Yeah,
interesting.
But that's an amazing experience. I think that at the time, complexity theory for quantum is really exciting.
Yeah.
Or maybe because there isn't too much you can do.
Right, yeah.
in that domain.
Just sit in a room and think about it really hard.
Yeah. So I spent a lot of time in my PhD thinking about all kinds of complexity theory. So, there's things about a quantum interactive proof system, and then there problem about how the entanglement between systems can give different power to complexity system. At that time, I was working on QMA2. quantum Merding also problem with the two provers. I had some result later with both Yaoyun and also in my PhD I had the result with Aaron and Anand. That's my postdoc at MIT. So that's what a topic really excites me until to the point I think people see new possibility for other type of things. So I worked a little bit on crypto, especially device independent crypto at the time. They call it certified randomness by nature laws.
Right.
Yeah. So that's actually a topic picked up by Yaoyun and there Carl Miller, who is also a fellow at the Quicks now, was working with Yaoyun on that topic, and I was also got interested in that. So we have a few projects looking into the crypto stuff, especially about the randomness generation.
And did that include sort of quantum sources of randomness?
Yeah, so I think this is something super interesting from physics or some philosophical perspective.
Yeah,
it's really talking about whether the nature is deterministic,
right,
or you have inherent randomness inside it, right? And if it's the case, can you really certify that there is such thing?
Right.
And then the device.
It's funny, isn't it? Because on the one hand, it's just a mechanical. There's a need for random numbers to generate cryptographic keys, etc. But on the other hand, it's like an ontological question about the universe.
Yes.
There is such a thing as randomness or not.
So, but of course, we come. I think a lot of physicists also started this topic at the time that was a hot topic. It has fundamental I'd say physics and philosophical interest, but also can lead to something practical, right? So random number generators, and that's basically the key for building really secure crypto system. I remember even see the certified randomness this year our Nature paper with JP Morgan running in some continuum, but using the theory from Scott Aronson and his team.
Right.
But that time we're really looking for something with much higher security guarantee because it's a theory paper.
Right.
And we try to see without trusting anything about your devices, just looking at input output, what you can say. It turns out, we after a few papers, if you don't have that, we know you just need a little bit of randomness to start with, and you can certify tons of randomness out of the devices. I don't know whether that's something practical,
right?
But from the foundation's perspective, this is really amazing, right?
That's
so
cool.
They say either the world is a super deterministic, so nothing really is random, or you can just spend a little of randomness. You can certify basically infinite amount of randomness out of the world.
That's interesting.
Yeah,
that's an interesting result. So that was during your postdoc at MIT.
Yeah, so that's really near my graduation as PhD, and also I spent most of my time in my postdoc working on this. In addition to the complexity theory I just mentioned. Right. Yeah. So that basically summarizes what I have done in my PhD and in the postdoc.
Right.
Yeah.
Right. And then you landed at UMD.
No, I spent 2 years in Oregon.
Oh, okay.
Yeah, before I joined UMD. At that time, there also the job market for quantum is pretty bad. Because
Dave Wineland is at Oregon now.
Yeah. I think Oregon has a very good experimental physics. Yeah. And now Dave Wineland actually he moved to Oregon after I left.
That's too bad.
but I know he actually has a lot of connection. He had a lot of students at Oregon. Yeah. So I know that. But just at that time, quantum computing wasn't really a really hot topic,
right? And
still very niche, and people don't know why they want to invest.
It's only slightly less niche now, I would say.
Yeah, but
it's a lot more, but it's still slightly niche.
Yeah, I won't argue with that.
Yeah.
But just there's national interest in that. Definitely there are also tons of progress both in
absolutely.
industry.
That's the exciting thing is how much has changed in the last 10 years. It's incredible. Okay, so Oregon and then UMD.
Yeah, but that's the time my research interests start to just shift.
Yeah. In what way?
So I think this is a very from my inside this is really something I had from my education in undergraduate, especially as the physicist student. Not just pure as a theoretical physicist. I always remember the professors that have been teaching us courses just say like you should need to have like a two feet for like studying physics, right? So you need to understand theory, but also you want to see the experiments,
right?
You want to see something real, but otherwise you're doing mathematics, right? So and of course mathematicians they're great,
sure, yeah.
But if you want to understand the nature, you need to have both,
right?
So I think I've done a lot of theory. I really want to see how quantum computer can work in practice, and and part of the reason I can probably see a little bit more than other computer scientists because I have a physics background,
right?
So I didn't do a physics PhD, but I can try to understand what's really going on, and I understand those physics still fascinating to me. So and of course at the time people have the technique has matured to the stage where you do see some early prototype of quantum computer appearing. And then I actually spend a lot of time looking into that, and also need to think about what it can do. So that's like one motivation for just stepping out of just pure theoretic study, try to see what's possible. But still, it's different fields. And another motivation is that I actually had my undergrad advisor visit me in Oregon once. He used to work on the logic, but then formal method, program language, this kind of stuff, and he moved up to work on this part of things for quantum. And before his visit, I wasn't really sure what one people can do, outside theory for computer science. But I think he just showed me there are a lot of interesting things that one can do, but not just only one can do, but one needs to do, right? So in order to make the computer really working, for like the user to use it, and there are many other things than theory, because theory you study like very abstract, clean mathematical models, you understand something in principle. But if you want to make things work, there are many other things you need to do.
Well, and is there a sense also that, experimental physics makes devices that embody a particular experiment. Computing science makes a general purpose machine. And there's sort of this phase of interplay between sort of experimental physics right now and computer engineering, in a sense, like to help the physicists build these larger scale systems. We sort of have to blend physics and computer science, just like you were saying.
But it's also interesting to just learn the history. So because I think I definitely too young to know anything about history if I don't really spend time in looking into that, because nobody's really teaching a lot of things we have done in the past. But if you look into the history, you're going to see we probably start with like a special purpose machine,
First, even classical,
even for classical, because people need to kill it up, right? People need like the resource to build that. They know when we build that, this can be put in some use case, and then you get the financial support,
Well, and it was physics experiments, in fact, right? I mean, ENIAC and von Neumann's machine in Princeton were both accelerators for physics computation, physics-based computation.
So basically for scientific, computation at the very beginning. But people will buy that. Right, so they has utility, and I think this is something I learned, especially after I joined Amazon. I didn't really bring the economic into the picture. If I'm not really stepping into the industry, I thought everything is academic. We solve the problem, nice, but then you realize if you really want to solve the problem, you shouldn't forget the economy side of everything, because you need those resources, and you need users, and you need people to invest into this, and then nothing will happen without any of this, So but anyway, I said that's the fascinating thing I didn't know in my PhD. I get into maybe other part of computer science, and then going from there, I see not just computer science, maybe like electrical engineering. And I basically look into everything we probably need in order to build our classical computers. That's not something people are teaching. You need to spend a lot of time, really think about how this happened in the history. Of course, I really want to have someone really teach me how this happened, or how since technology just pivot from one to another, So, and what's the motivation behind that? It could be technology, a reason, or maybe because there's some like other economical reason, So, but you do see
like market driven or technology.
They're definitely not like one straight line, So there has been many pivots in different in both the way you build the classical computers and the application
Right.
in the targets.
Right.
And
Right.
so many things you can see. Of
Yeah.
course, I still don't have a very good answer or understanding for everything. But you see, this is very complicated.
Yeah. So you draw on the lessons of classical computing to sort of identify areas where you might want to do research. Is that sort of how you're using it?
Yeah. So I mean, of course, the field is huge. It's like just embodying the entire computing industry.
Yeah.
That's huge. I'm not saying I know everything.
No.
I just say, okay, I just realized there's so many things that I don't know. Well, that's always a good thing for a researcher, right? So if you have your own curiosity, right? So you want to know, there are so many things you don't know, right? So you want to just pick something to learn. But of course, I cannot learn everything. Especially my undergrad is background. The knowledge I learned in my PhD somehow limit what things I can explore. I only can explore things one by one.
Yeah.
Maybe gradually enlarge the scope of those things I'm doing. But for me, I think there could be some like random walk into the field, but also I feel if you're looking into what the quantum computer is one day they can be a reality. What are the necessary parts are there, but what are the missing parts for today?
Right.
So indeed, there are actually many. They're not just one, right? There are many. But just to start to pick something that I think I can, it's more tangible for me to get started. And the first thing I get into is, outside theory is doing program language. I actually, I think I learned a lot by, but just the understanding the field. I still don't think don't treat myself as an expert in that field. I mean, I think there are tons of other classical, knowledge about program language that I don't know. But I gradually to see how that community think about things, what they think about the computer science, for example, and what kind of research they think they'll be important.
Did you like start to design your own quantum computing language, or were you using existing tools that were out there?
I mean, I'm not starting with designing my own language. You probably just mentioned SimiQ. I can get to that point later.
Right.
Yeah. So I didn't start with doing my own program language because I wouldn't know why I want to start design a new one. Right. So I start with some still a technical question. And I think that technical question is I shouldn't say that's like a first principle type question because there's a lot of technical questions one need to address. The one I get started is to really helping people see how they can verify the quantum program they write is correct.
Yeah.
And before I really get to the point, I didn't know actually debugging testing is a big market.
Yeah, right.
in practice, companies spend tons of resources just to help people write the correct program.
Yeah.
So that's the first time I realized, okay, human factors is a big thing. Before that, I said, okay, mathematically this works in principle.
Right.
How can you make things wrong?
Right.
But then I realized, okay, if you really want to build this in practice, you need to deal with human factors. Or not just human factors. Sometimes just it's so hard to make things correct, even you can do this in principle. Right. And then we know there's bigger failures of larger projects.
Theory experiment.
I wasn't really appreciating that until the moment I get to the field. I see, okay, people are making that mistake. Actually, you should assume that will be happen.
Right.
That's something will happen. Not assume this won't happen.
Right.
I think that's a big change of how
that's interesting.
View about the different assumption from
Yes.
But that's still a challenging problem, right? So we have something, think about, basically try to see how classical techniques for really helping people writing correct software can migrate to quantum. I think that's maybe still a bit too far from what we currently have. We don't write super complicated quantum software for now. But research
it's coming though.
Research is a little bit to the future.
Yeah.
Right. So
exactly.
So we have some proposal for how you do this. Maybe using a Tony Horse way. There's a hard logic for verifying the correctness. But then there's also a very formal method way, right? Writing the software, doing something people call correct by construction. So that's actually related to the automatic theorem prover. I think this is just get hotter in the general audience now because Tarantau says you want to do this for also verifying the proof for mathematical in the papers. But at the time people show you can do this to verify your software is correct.
Interesting.
And that's people call correct by construction. And we basically find out there are many classical techniques for testing, debugging.
Right.
They don't really extend to quantum, but the corrected by construction approach they can extend. Although that's expensive. So nothing really, practical implication for now. But we do know if you want one day, there's certain quantum software you want to have 100% confident that is correct.
And that might be really critical once we get to the size of system that you can't simulate classically at all, right?
Yeah, exactly.
You have to sort of fire it off into the quantum computer, and you don't know how to actually track its progress.
Yeah. So you know what people do for this in classical domain? They write such a same for GCC compiler because compiler going to be used a lot.
Yes.
You don't want a compiler has error. Actually, the GCC compiler has a lot of errors. And then people write this for operating systems. And because those are the very core software package, you have to have 100% correctness, especially if you're running this, say, on Airbus, right?
Yeah.
So on maybe either Eurostar train. That's actually super impressive. Those research they really have in application in real world in a very critical way.
Right.
And I think quantum computers should be added to the list. When we have the large system, we want to have 100% correct core part. I think that time, my research can help.
Yeah, that's
but
interesting.
Of course, it's still far from there.
Yeah. So what about? So that's sort of the long term. There's stuff that you've been doing that's more about how to get value out of the devices that are being built today, right? So what are some examples of that your group you're getting?
So I think this is just to connect to the how what kind of other topic I pick up along the way. So I talk about the first topic I do in a program language, but then if you're doing that nothing is cooler than if you have your own language, right? And actually we see there's so many different languages. And what really inspires me, at the very beginning, I say, okay, how, am I really in the position to create something new as a program language? You will say, okay, maybe you're just a single person. You're not a company, right? You don't have enough workforce, and you're not say have done tons of we don't have tons of application either, right? So what makes you think there's some way you can make a new program language, and maybe that program language will be useful? And then what really changed, my mind is that I'm really happy that when I start working on this, and there was a conference, in the program language community. They called the history of a program language. I think that conference only held every a decade. But when I started, there one, and so the purpose of doing that, they just have people writing about how the famous program language in the history, either popular in used in industry or not so popular in the industry, but people think that provide you a lot of conceptual sense. They try to have people try to say what's the motivation, why they build that, why this is important, and why this changes some field. And actually, that's the time about the COVID. That's really pandemic time. You don't have a lot of other things to do. I don't need to teach, for example. So I have the luxury to really read through basically almost all the survey paper about a lot of existing famous program language for some reason. I think I learned a lot by just reading that, because that's really give me a very different idea about that domain, right? So why people think certain program language is important in history, and I think that message was later amplified by the Turing Award, and I forget which year, to the compiler, Aho and sorry, who's the second one? Maybe you should help me.
It's
the second one. So to give a Turing lecture, they really emphasize, the abstraction is important and a really powerful tool by computer scientists to help people, basically solve all kinds of tasks. Some of the tasks, they don't really like a computing task, but we can solve them by computers. So really building the right abstraction. think about how you can not just have abstraction to think, but also out of those abstraction you can do automation. You can compute on top of that.
Right.
So that's like I think very powerful.
That's one of the things I find so fascinating about this stage of quantum computing is that classical computing, you look at your phone or your laptop, that's 70 years of abstractions, right? I mean, there's so many layers, as you said, so many pivots. Some of them are technology driven, some of them are marketing driven or market driven. And with quantum, we have almost no abstraction at this point. I mean,
I think we do have abstraction. It's hard to argue whether that's the correct one, but probably we don't know what's correct one.
Right.
But I think that's fascinating to think about.
Yeah.
So I think the more I think about the problem, the more I talk to other communities about that, I realize people do. They do want abstraction, but they have different expectation for the abstractions.
Right.
So I think from the program language perspective, you basically want to have a way easy for the users to really program your applications.
Right.
And you don't just program in Python or like C. Actually there are many other program languages, especially for certain domain. If you want to do modeling, simulation, or other type of thing, for machine learning, you have tons of different abstraction that help you to solve your problems.
Right.
But of course, for quantum, we don't know what's the killer app yet, so it's hard.
Yeah.
Right. But on the other side, you see, at that time, I think it's still possible. A lot of cases still the same today. Even though I should say there are a lot of progress, from other people. But if you look at what we have, say, Qiskit or even bracket or circ, other sense, you see this is really like some Python way for writing down our circuit.
Yeah, exactly.
And I call this like a Python based or maybe 21st century punch card.
You're right.
Right. So
yeah.
You definitely it's more automatic. You have very nice UI, right? So you do this on your laptop, but you're just doing punch cards.
Yeah.
Essentially. And of course, I'm not saying you shouldn't do that because we start with the punch cards for IBM machine like in the old time. But what really drives IBM to a success at the time is that people they realize they cannot just stay at the punch cards.
Right.
Right. So they identify the application. They try to see how to connect. Make things easy for the domain users. And that's the time they invented Fortran.
Right.
And that was a huge success in history, even though not a lot of people using Fortran today.
Yeah.
Right. But that give you some things to think about, right? So can we invent something like Fortran? For quantum? Again, I think that the real challenge for thinking that way for quantum computing is that we don't know the killer app.
Right. But we have some guesses of where the first use cases are going to emerge.
Yeah, I mean,
right. Feynman had a really good guess, and we're pretty sure he was right. That stimulating nature is probably going to be what quantum computers are good at.
Yeah, that's actually exactly the point I'm going to mention about. Right. When I say we don't know the killer app, is that I'm not saying we don't have proposals.
Yes.
We just say we don't know those things will really maturize, right? So you for the classical domain, when you build a computer, you want to do something.
Yes. Yeah.
And somebody will pay for that. So that's not a big issue for them.
Right.
But now, like you said, the only thing we know for sure is that you can simulate, quantum physics.
Right.
That really, wasn't really like a computing, for many computer science, but still, I think that's a valid point, right?
Yeah.
So quantum computer can be used to simulate quantum physics, and there are tons of interest from, the science community to see how we can make use of that.
Yeah, and advanced manufacturing. I mean, you can see Airbus and BMW and LG and Hyundai, like they're actively exploring what they will be able to do as for improving inputs into their manufacturing process or their products and
exactly. Yeah. So I don't think there's any doubts in the large community that people say quantum simulation wouldn't be application case. Actually, this will be the I think the least controversial cases. People will say quantum computing can be good at that. Then that comes to me as to say this actually is a safe choice, right? So you know something you want to do. Can we build abstraction around that? Right. So that's to me is that I know I want to build abstractions.
Right.
And there's something I can definitely try, and it's a safe target, and it also exercise for me. Yeah. So I then that start many things, not just in program language. I basically try to see can I help people to think about quantum computing, both the way you use the machine or the way you design applications based on the Hamiltonian abstraction. So this is slightly different from the gate abstraction. The gate abstraction, we have that for a long time. I think there's good reason to think about gates, but they also I think scientific reason is like super clean mathematical model. There are a lot of things you can say, especially in complexity theory. You have a way to count the resource gate by gate. So if you don't have a way to measure the resource, there's no way you can build a complexity theory.
Right.
But Hamiltonian is something hard to build some measure that is agnostic of the hardware. But on the other side, you say Hamiltonian is so natural, right? So can we directly think about Hamiltonian because it's close to our target applications, right? So it's a higher level abstraction, than gates, and the potential also closer to your implementation because when you try to implement your quantum computers, you still run Hamiltonian. Right, you use the dynamic to do something.
Right.
Of course, a lot of people know how to use that to do gate, but also we know there are certain Hamiltonian you can do them directly. Maybe with better control, you can do them very faithfully. So I think that time essentially the Hamiltonian simulation or Hamiltonian self is a good target. But
in some ways, it's the Hamiltonian. I mean, like the QERA system, for example, they don't implement gates yet on the Aquila system. And they talk about it as an analog Hamiltonian simulation. So is a Hamiltonian almost more analog in nature and gates are more digital? Is that a useful distinction? Or
I think that's something I don't think I have the final answer. Like I said, I read into the history because for me, I didn't know all this idea. So I know people have their own opinion about like analog digital, or what's the difference. But for me, the first thing. This also works in when I try to develop abstraction. I want to look into the history, like I said. So I feel there are good reasons and bad reasons for using either of them. But then it's really not a debate for which one to use. It's more about like which one is more suitable, for the technology you have. Right. So and something I learned from I still say limited reading of the history is that the analog thing they're cheap, right? So they came early and they have been used for some of the tasks in the history. I think some of the Apollo project you make use of that. And they're still, they can be very useful for doing a lot of signal processing as well.
Right.
But of course, they're not precise.
Right.
They're like more like noisy sensitive.
Right.
And it's super hard to control our analog machine for a very long time.
Yeah.
Right. So people know what's good and bad about it. But then also, of course, for digital ones, you can do something super precise.
Right.
And you basically lower the control task. Right. So because now you just need to implement a single gate. And you do that gate well, and you can have tons of gates to give you something you want.
Right.
So basically, I think that's a reduction of the difficulty of control the entire thing into the controlling of a single thing.
Right.
Plus, you can scale them.
Right.
But once you can scale them, then that's going to be something you want to do, right? And also, digital sense give you more generality. So that means I just need to build this one thing. I can do many other things.
Like Lego blocks.
Yeah,
you can build anything out.
Exactly.
Yeah.
And of course, because of the moral law, this becomes super cheap now.
Right.
And people just use that.
Right.
And I'll say, we're, for most of us, people in my age, maybe, younger than me, we probably haven't seen anything analog your life, right? So, it's really hard to try to convince you why there's still value of that.
Yeah.
Right. So, but actually, if you look into more about the reason about why something is good or something still has a limitation, and like I said, the assumption for digital is that you need to be able to do them, a lot of gates, right? Very cheap, cost.
Yes.
And if you cannot do that, then you run into other troubles.
Right.
I think this is something you really like. This digital is a model. In principle, you're gonna work. And you can build a gate today. Wonderful, right? So you have a clear logical path leading to the ultimate goal. But the difficulty is actually how you scale them.
Right.
So it's not something you see right away.
Right.
You just push the difficulty, conceptual difficulty into the future. You say we can handle that. Maybe we can.
Maybe.
Moore's law says there's a lot of things you can do. Integrate circuits, right? And then whereas design, you pushing to the size of your transistor in your chip, right? So that happened. But there are many other reasons to make that happen.
Yeah.
Are we, ready to get that? I don't know. Or how many years we need to get that? I don't know. But on the other side, analog saying something cheap.
Yeah.
Maybe you can find some application for that. And maybe it's more suitable before we, have our digital ones.
Right.
And as I said, maybe that's something we can find the first useful applications.
Right.
I don't know.
Yeah.
So and I also say, someone should have started that, right?
Yeah.
And when regarding for in my case, I try to make some abstraction and basically change how people think about that. Then whether you implement that in an analog way or digital way doesn't really matter to me, right? So
the abstraction is still the Hamiltonian. The implementation could be either.
You can do either way.
Yeah.
I don't care. It just I think that's the power of abstraction. So what I want to do is that can I think about the whole quantum computer using abstraction that based on Hamiltonian? And of course, they're good way. There are problems that you don't want to use Hamiltonian as abstraction.
Right.
So I'm not claiming this is something you want to do always.
Right.
And there's certain a lot of existing algorithm about the discrete problems you don't want to use Hamiltonian to think about. So for me it's more like what are the good use case for Hamiltonians? When we think about Hamiltonians, can we think about something new that is really hard to perceive if you just think about circuits? I think that's the question I try to address. I'm not saying Hamiltonian is everything. No, I can totally see it cannot solve all the problems. But I really want to see what this kind of abstraction is good for. And can this kind of abstraction lead to something new that is hard to think about in the circuit model?
And so you have released this early version of this programming language, right?
Yeah.
Would you call it a programming language, or is it a framework, or how do you sort of think of the code that it's SimuQ is the name?
It's SimuQ.
Yeah.
So like I said, when you think about abstraction, you have many things you can do. One thing, of course, is building the program language tool. And I also have projects say using this kind of abstraction, we can think about new applications, and we just prove things there as well with this kind of new angle, which I think it's really hard to think about if you were not using Hamiltonian abstraction.
Right.
Using circuits, there's no way I can think about that. But just
what are some examples that are use cases that yield themselves to the Hamiltonian abstraction better than the gate abstraction?
Yeah. So that's actually has something to do with the problem with the continuous nature. So as you can see, what the gate is good about, this is both true for quantum and classical. We know definitely a lot of things about classical. They're about digital design, and everything boils down to Boolean functions. And it's actually that's the beauty of the digital thing, right?
Yeah.
It's super precise. Digital is very error resilient. But you just you have a lot of tools to deal with a digital sense.
Right.
But there are a lot of applications they're continuous.
Right.
For example, machine learning today, right? So all the training,
Yeah.
And they're continuous optimization problem. The weights are continuous, and actually you want things to be differentiable.
Yeah.
So that's one example of continuous, and there are tons of examples say in scientific computing.
Interesting.
Like PD solvers, people want to model real problem, like an engineering problem, mechanical problem, or even problem in nature, right? So a lot of the models they're continuous.
Right.
So they're not digital. Of course, if you have a really good,
you can create a digital
machine,
model,
right? So you can create a digital model,
right?
And mimic the continuous nature.
Right.
I think it's still super fascinating. I think a lot of people don't really realize that we have finite precisions in your computer, right? So we have limited digits in whatever, floating number or whatever.
Yeah.
So
I always think of it in terms of media, like music, for example. We just sort of go to 44 kilohertz, and past that, your ear can't really hear it. So who cares, right? So, but it's still, you're dropping all kinds of information that's there. It's just not relevant to the use case of listening.
Exactly.
Yeah.
So I say this is fascinating. Right?
Yeah,
so we use floating numbers with digital machine. We can do a lot of things continuous in the classical domain.
Yeah.
Right. So I think this is really, really great. But of course, we don't have this kind of thing for quantum. We don't have enough gates.
Don't have enough gates, yeah.
The question is that if we think about problems that will be more natural, they're continuous nature,
Right.
And
You mentioned signal processing and analog classical ratio.
Yeah,
so
I think there's even something very fundamental like a gradient descent. So gradient descent, people know, that's one magic box, behind all the ML stuff.
Right.
Nobody know why it works. It works, right?
Really?
So the gradient descent help you, SGD, right, or Adam, this is a basic training tool for deep neural networks.
Right.
Deep neural network definitely not convex function, right? So there's no theoretical guarantee you can get somewhere, but it works pretty well.
Right.
The gradient descent help you to identify reasonable models.
Right.
With maybe tons of computing power.
Right.
So I think that's still a magic. Nobody
Yeah.
has a very good theoretical explanation. But if you look back, gradient descent is a very fundamental algorithm. It's a fundamental algorithm, I think, both in theory and in practice. And if you think about the circuit model, it's pretty hard to think about, what will be the quantum version of that, right? How you think, gradient descent is a so simple algorithm classically, right? So how can you make a quantum version of that? And presumably it should be having some new quantum feature, and hopefully it should be better than the classical gradient descent, or maybe also the many other classical algorithms for some tasks.
Right.
So I think that's just one example why I think switching to think about Hamiltonian really helps, because if you don't think about a circuit, you don't want to say I want to design an algorithm by a very clever combination of the circuits. Then you say, okay, how can I, maybe there's a way I can rethink about the algorithm in continuous nature. Say like a gradient descent. What this really is, this is really just a dynamical system. Right, it's a classical, very spatial dynamical system. It can help you, drive you to say the point where like a gradient zero, right? So people call not necessarily always even to the local minimum, but going to but it works so well. Right? You can think this is just a classical dynamical system. And that's basically the reason we can think about the quantum version when we move into thinking that way, right? So if you have something it's a classical dynamical system, then you can say maybe I can design something that is a quantum dynamical system that has some kind of connection with the gradient descent.
I see.
And I think that's the big conceptual step we had.
And in SimuQ, have you actually sort of done a quantum gradient descent, the equivalent of it?
We actually has a software package implement that algorithm on top of SimuQ. So SimuQ is it's more like I say, it's abstraction for the users, right? So you want to say I just want to do some kind of Hamiltonian simulation.
Right.
Can I write a simple program to do that?
Right.
So what would be the simplest thing you can do? You basically, if you say your domain users, you're a physicist or material scientist or whatever, you write down your Hamiltonian. You say, okay, quantum computer help me figure out how I can run this Hamiltonian.
Right.
All I want to know is some property about this Hamiltonian.
Right.
So, and I basically give you a way to model what you want to do. And I think that's really inspired by there was a program language called Simula. And the Simula, the got a Turing Award, by the way, around 2000. And it's really the first type of modeling language help people to model probabilistic system, especially the queuing system at that time. Help people to write down the probabilistic model and simulate that. Of course, people will compile that to say, I think Algo 60 at the time, or maybe later on to maybe to Fortran. But it gives the users a super clean abstraction.
I see.
All you need to focus on is your problem, and your problem at that time is say, just tell me the configuration of your probabilistic model, and the program language or the compiler will do the rest for you. So I developed something, very similar to that. To basically say, from the user perspective, this is the Hamiltonian I want to address.
And it's open source, SimuQ.
It's open sourced. I think we have done the first version compiler. We built the interface. So basically, we put Hamiltonian as the first class object. So if your task is something to do with Hamiltonian, it's super easy for you to write the program.
That's cool.
right? And then the compiler will handle how we can actually run that particular Hamiltonian. And you can actually we built a prototype of the compiler. I shouldn't say this is something really great, but we showed this is possible. We can compile to a few of the existing machines through their like public APIs. We done this through Bracket.
Right.
We can connect to Qiskit if you have the IBM access. We do this. We can also have this through D-Wave, and we also have connect to this to Qtip if you want to simulate that.
Great.
So we made this connection. I think there has been some follow-up work to improve our compiler. I think definitely there are a lot of things you can do. But I really see the values that we build a different abstraction of its own kind. It's something really good for the task if you want to simulate Hamiltonian. That's your major task. Then maybe in the future you can build a more like user-friendly language on top of that. But we showed this direction is possible. And like I said, like we actually also added to some new application here, not for the nature science purpose, for something computational.
Right.
So,
and which is bringing you back to where you started, which was you wanted to find a way to combine physics and computer science, and you have.
I mean, hopefully, I think this is still our proposal. I don't think it has been widely accepted as something. We think it's. I mean, I have strong belief in that, but I think I still need to, convince the community,
the broader community,
and also of course by doing that, also just try to see whether I can convince myself or I see something wrong with that, and of course I can pivot.
Of course,
So, but so far I see compelling evidence. So, but just coming back to that, so we have a program language that help people to run their Hamiltonian-based applications. I think the major contribution for that project is we show this kind of abstraction can work. And we, in that project, we basically show, you can reproduce Nature papers, all the figures with just like maybe 200 lines of code.
Wow.
And actually, the language is not designed for the Nature paper.
Right.
So we just say, this is a good abstraction that can save you a lot of effort, and also, you basically, really. We try to sit in the shoes of those domain users for this, right? So if you really think about Hamiltonian simulation is your task, you should find this language pretty easy to use.
That's great.
Yeah, and of course, how we can make the compiler works. That's taking a good challenge, or maybe there's going to be some balance between how you can decorate more information in the language pass through the compiler, because compiler is not super intelligent.
Right.
But I think this showed that direction is possible.
Right.
Yeah.
Right.
So, and I can totally see if we identify a killer app, for quantum computing in the future, where Hamiltonian simulation will be a major part of it.
Right.
You can definitely borrow ideas
from
this project. I'm not saying you should use it.
Right.
It's actually a lot of cases in the development program languages that you prove something.
Right.
The concept
and
is
those
useful.
ideas get incorporated into
the language itself, they might die, but the idea will just exist for a long time.
That's fascinating, Xiaodi. That's great. I've been very curious about the work you were doing in SimiQ, so I'm glad we did sort of a deep dive into it. And hopefully, if people hear the podcast, then you'll get some inbound interest. You'll get some more adoptees, and kicking the tires, so to speak.
As I said, this give you like more conceptual ideas. I think as an academia group, usually it's not the case that we can maintain a really large user community in the program language. We just shorthanded to do that.
Yeah, of course.
But I hope the future developers from either industry or maybe academia, they find this concept useful.
Right.
And they can grow their own program language, but they can use our some of our concepts. I
That's
think
great.
then that'll be super happy. Yeah.
Awesome. Well, thank you very much for your time and for telling us about SimiQ and your journey. So I really enjoyed it. Thank you.
Okay, thank you.
Thank you for listening to this episode of The New Quantum Era, hosted by me, Sebastian Hasinger, with theme music by OCH. You can find all past episodes at www.newquantumera.com or connect with the show on Blue Sky at newquantumera.com. Special thanks to the organizers of IEEE Quantum Week for their support of this episode, and to Xiaodi Wu for sharing his insights and experiences. If you're enjoying the podcast, please subscribe and let your quantum curious friends know about us. Thanks again for joining me.